Welcome to the 2015 NASA Ames Summer Series. The world around us contains materials that can be divided into solids, liquid, and gas. These descriptions of the state of matter are relative to the particular time span being observed. Given a long enough time, all matter exhibits fluid motion. Understanding the interactions between these different states of matter is important for optimization of design and function, specifically when you talk about work that is done in aeronautics and space travels. Today's seminar is It's a Fluid World and will be presented by Christina Ngo. Christina received her Bachelor's of Science in Mechanical Engineering with a concentration in aerospace from the University of California, San Diego in 2013. But prior to that, she was also here at Ames as an intern in 2009. So all the interns that are in the audience, think of the future. During the internships, she got experiences both in work and as an intern in aeronautics at Pratt & Whitney, at Hamilton Sunstand, and SpaceX. And then she decided to come back to Ames. So she joined the Fluid Mechanics Lab as a research engineer 2 years ago as a full-time employee. And so please join me in welcoming Christina Ngo.
Hello, my name is Christina Ngo, part of the Fluid Mechanics branch. Today, I'll be presenting It's a Fluid World. So about 6 years ago, like Jacob mentioned, I was sitting exactly where you were sitting as an intern and thought to myself, man, it would be great one day if I could ever be up there. And honestly, I never thought I would ever have the opportunity. So word of advice to all the interns that are out there today: work hard, ask questions, learn a lot. You're surrounded by some amazing people. Really take advantage of your internship. So let's begin. So during this talk, I'm going to show you some of the hot research topics that we've done in our branch currently and in the past, as well as how aerodynamics applies to the world around us. Here you see a lot of interesting photos. It's basically a collage of a lot of the research topics that we've done in the past, anywhere from space shuttles to rockets to even sports balls, next generation airplanes. In our branch, we are investigating the flow around our models, whether that's on the surface or off the surface of the model. So how many of you have heard of a wind tunnel? Majority of you, great. So for us to investigate all these parameters, characteristics of the flow field, we have to look at it sometimes instantaneous in time. So it's really difficult to measure these characteristics having, say, a rocket going up several hundred miles per hour through the atmosphere. So instead of having having the model moving over the air, we have air moving over the model, which is why we have wind tunnels. There's several of them shown here. Top left, we have the 40 by 80 wind tunnel, and next generation airplane shown. Top right, we're home to the world's largest wind tunnel, parachute testing right over here. We even have smaller scale wind tunnels, like the 11 feet by 11 feet transonic wind tunnel, testing a plane as well, and sports ball aerodynamics. Really great things we need to do, and the majority of research is done in wind tunnels because of this, of course. So I talked a little bit about wind tunnels and how we use air to move over our models, but we could actually use any fluid. Here we have a facility called a water channel, so we're moving water across our model. So how does this work? Well, we have an upper channel and a lower channel, and the water moves from the upper channel through our test section back down to a lower channel. It gets pumped back behind here. That's not shown on the photo. We're able to put small-scale models in here. Once that is done, we inject these fluorescent dye, these green lines that you see, that's illuminated by UV lights. We have a second color dye, it's the orange dye, that we use to inject in places of interest, say in the seat of a convertible, or behind a sports ball right over here, or even behind a hill. So it's really great visual technique to start, instead of using really expensive computational techniques or advanced instrumentation before we even begin testing. But what better way to explain it than actually showing you in action? So here you go. We have the fluorescent dye flowing from left to right. It's the green dye, and we injected the orange dye in the very back here. What's in this test section is the hill. We call the fundamental Aero Investigates the Hill, or Faith Hill. What's great about this dye, this feature, you could actually see exactly where the flow is separating off the model, right over here, in the vortex shedding that's coming off of it. Even though this hill does look quite simple, it's a cosine hill, the flow is actually quite complex. And with this hill, we use all of our experimental technique to measure the forces and pressures on the surface and on top of the surface of the model to validate a lot of our computational method. Again, here you can see how complex the flow can actually be. See the recirculation area, and the flow behind there, it's almost stagnant. It's barely moving. One technique that we use is fringe imaging skin friction to measure the skin friction on top of our model. Here is Faith Hill again. And how does this work? Well, let me explain skin friction first. Skin friction is a force that parallels the surface of the model. So we have a model, and it has to be shiny for this to work. We install this into a wind tunnel. We turn on the wind tunnel for a certain amount of time. Remember to apply oil of known viscosity. Once the wind tunnel runs for a certain amount of time, those sort of smears around our model. Once that is done, we illuminate the model with an extended monochromatic light source. You get two interfering light waves when that happens. First, the light reflects off the surface of the model, so that's one light wave. And then second, the light reflects off the surface of the oil, that's a second light wave. And you get these fringe patterns that you see here. And measuring the direction and the spacing of the fringe pattern, we could actually correlate that with skin friction. So remember the video I showed you before where the flow starts separating and speeding up? You could see it in here as well. It starts speeding up and the skin friction increases. And once the flow is stagnant and slow on the very back, skin friction is actually really low right back here. Another technique that our branch excels at and spends a lot of time in is pressure-sensitive paint. So originally, normally, we install our models with discrete pressure tap or pressure holes, like you see here in one of our crew exploration vehicles, Orion, these tiny holes to measure pressure. And for us to get a nice contour surface pressure map, we had to extrapolate the data, which sometimes could cause a lot of error here. So with pressure-sensitive paint, you pretty much get a pressure tap or pressure measurement at every pixel of the picture. So you get a whole map of the pressure surface without even extrapolating. It's a very powerful technique. Well, how does this work? This pressure-sensitive paint is first painted on top of the model. This is nice pink color here. It's pretty cute here. And there's these molecules inside the paint that are excited by UV lights. For them to return back to the base state is via oxygen quenching, which is great. Because the higher pressure you have on the surface, the more oxygen there is. Therefore, there's more quenching and the less luminescence that's picked up by our cameras. And we could correlate this with pressure to give us a nice contour map that you've seen on the right. A few examples I have is on a space shuttle right over here, going Mach 2.5. So Mach 1 is the speed of sound. Right now, it's 2.5 times the speed of sound. On the bottom right, you see an F-18 going Mach 1.25. Another great advantage of pressure-sensitive paint is you're able to paint surfaces where you probably couldn't instrument, say where the wing attaches to the body or the tip of the nose. Right? Here's a video of changing angles of attack of an F-16 model. You can see how the pressure is changing. Say if I'm running a computational method to see the surface pressure only at angles 0 and 1 or 2 degrees, how would I know at the higher angles of attack to install a pressure tap right here, and that's actually an area of interest? You wouldn't, but with pressure-sensitive paint, you don't need to do that. So we talked a lot about pressures and forces on the surface of the model. How about off of the model, the flow field off top of the model? Well, we use a lot of our optics technique. One technique we use is particle image velocimetry, seen here. We use a laser that's shined into a circular mirror and produces this laser sheet right across the model in our wind tunnel. We need windows for this, right over here. And using pulsed LED lights and 2 cameras and injecting, say, smoke or known particles into the flow, we're able to track these particles through the laser sheet. So we know dp, the position, and the time it took for it to move to that position. Therefore, we know velocity, 3 components of velocity. This is a very powerful tool to validate, say, computational codes or looking at turbulence models. For the aero engineers out there, you can even see a bow shock coming off of the shuttle right over here, starting this really big jump in velocity. But why stop there? How about we taking multiple images to get a nice video that varies in space and time? So here on the top with a still image of a cylinder when smoke injected into a flow field, you get this vortex shedding. Same thing is done here, but using PIV. We have a cylinder right up here, and you see the vortex shedding moving back and forth right over here. It's 2 out of the 3 components of velocity plotted. Another imaging technique we use is called Schlieren. So usually we use air in our wind tunnel. And once you start approaching, say, the speed of sound, Mach 1, air starts getting compressed. When air starts getting compressed, the density changes. So using LED light source and high-speed cameras, we can measure the refractive index of how the light is reflected off through the density gradient and take this really nice image. Right here, we have a rigid model of a Mars Science Lab parachute going about Mach 2.5. Where it's extremely evident where the density is changing is around shocks. And you can see a nice bow shock right over here dancing around in front of our model. Okay. On with imaging. So one test that we've done is to look at just the plumes and take a nice image and see the details of what's going on. Normally, we have a picture like this on the top left. It's really saturated, and a lot of details are lost. How about what if we had different cameras around the same location with different filters? We're able to superimpose these filters, these photos together, each having a little bit of the last photo that didn't have, little bit of pieces of, of areas that we couldn't get before, and superimpose them together to get a really nice photo like this here. So we use this technique at a shuttle launch. What better way to use it? Right here, we have the 2011 last final shuttle launch. On the left is a normal photo. Keep in mind, the right photo, we use 5 cameras with different filters and 1 IR camera, or infrared camera, that measures temperature. So this part right over here, you could see with the different filters, but with this part on the shuttle that's coming off, none of the filters would actually pick that up. That is because we had an IR camera on this part as well. This technique is also really great looking at debris that's coming off of the model that we couldn't see in normal pictures. But using the same technique, we're actually able to produce really nice videos too, and I'll show you right now.
10 seconds. CLS is go for maintenance and start.
You can see all the details that we never could have seen without this technique. And even little debris that might be coming off, you could definitely detect in this better than this. Pretty amazing. So one big project that we've done the last couple of years was the Crew Exploration Vehicle launch abort. So in this scenario, it only happens during an emergency abort where we have to take our astronauts off the rocket and back home safely, and many aerodynamic aspects that we need to consider during this mission. Here we have Orion capsule painted with pressure-sensitive paint, and we have a simulation of a rocket right behind here. So we separate the capsule from the rocket, and we can look at just the density gradients and the shocks and the aerodynamic variation during that separation. Secondly, we are concerned about the abort motors right here, using high-pressure air to simulate abort motor exhaust, impinging onto the surface of the rocket, whether that be forces, moments, pressures, or even acoustics. On the right, you have a bunch of Schlieren photos. You can see the density gradients are right over here. They're usually shocks, and a nice shock in the front of the model over here, and a second shock right here. So why is this important? Well, where do the astronauts sit? They sit right here. So we need to understand very well what is happening during this process. Here's a Schlieren photo of the separation, and you can see the rapid changes and density, and how dynamic the environment is during this portion. So the crew capsule is removing itself from the rocket at about 10 Gs. That's incredibly fast and incredibly dynamic and a lot of forces going on. Here's a second video of the impingement using high pressure air to simulate the exhaust. One interesting feature to point on this photo is you could see these multiple shocks coming off converging into one, as well as the exhaust interaction with the second shock. You see a crossover coming over here as well. And we talked a little about acoustics, but how do you look at acoustics data using this? Well, we have a whole research team dedicated to aeroacoustics. On the top right, you have a 26% scale of a 777 wing right here. And right here, you have these acoustics array. There's usually several dozen to a couple hundred microphones in a predetermined pattern measuring this noise. With this technique, we're able to measure the magnitude and the location of the noise. So I would call it a sound picture. Once that picture is taken, you could superimpose this picture on the surface of the model, say here. Right now, you can see a lot of the noise coming from the leading edge, the slats, and from the trailing edge, the flaps right here. Nowadays, engines are getting quieter and quieter, so we need to reduce the noise of the plane itself as well. I always thought when a plane was flying over, it was all from the engine noise, but it really isn't. A huge amount of noise itself also comes from like the landing gear. Basically, anything with a sharp edge produces a lot of noise. On the bottom right here, it's something called an anechoic chamber. It's what we use to build our arrays and do some sound experiments. So what this chamber does is the walls are built up with these wedges that absorbs noise. So if you're testing something and you want to know exactly where the noise source is coming from, you don't have the reflection off the walls coming off and messing up your data or giving you errors. So that's what's done here. Majority of any experiment that goes up on the International Space Station needs a sound qualification test, and that's usually done here in an anechoic chamber. Here's an example of our microphones in action. We have the launch Abort motors full scale that was tested in Utah several years back. And here are the microphones that's measuring magnitude in this case. But a better visualization of this is seeing the launch Abort motors actually turning on. So I have a video for you as well. Imagine how loud it really actually is. And sitting right above it, right under it, could be detrimental if you don't understand the characteristics of this. So back in 2013, we went one step further. We tested this at a real launch for the very first time. So here is the microphone arrays. And to give you a scale of how big this is, it's about 10 feet by 10 feet. It's huge. Several hundred microphones are installed. And honestly, we just get one chance to take this data. We couldn't stop them and be like, oh, excuse me, could you launch that rocket one more time? I didn't get the right data. So a lot of engineering and work went into making sure it was structurally sound. We were able to get the frequency right and all the data correctly during this experiment. Here, I'll show you a video of what it looked like. The sound image is on the left, and the camera that's really close to it is on the right to better see what's going on. You can see a lot of noise coming from the nozzle itself. There's actually a duct that goes under the launch pad that comes out of the exit. And once it shows it again, you can see a lot of noise actually coming out of the exit duct as well. We have a water suppressant system that actually suppresses the noise. Have any of you seen a launch before? Well, probably majority of you, okay. So if you ever see the water system that's getting blown onto the launch pad, I always thought it was to cool the launch pad, but it's actually to suppress noise. And because of this test, it changed the whole system of how launches were done in the future after this. It had to be initiated a lot sooner to suppress the noise. On to more rockets. We have a huge group in partnership with Stanford working on liquefying hybrid rocket motors. We've done 41 tests here at Ames and over 500 ground tests overall. A lot of effort and work went into this. Here's some few advantages of this liquefying hybrid rocket. First, it uses a paraffin solid fuel than the normal HTPB fuel. It burns 3 times faster. What does that give us? Well, it gives us a more simple system to burn. Here, that's what the fuel normally looks like. You have no multiple ports for it to burn evenly through. Because it burns 3 times faster, we don't need the multiple ports anymore. We have one port where it could burn evenly through. And with multiple ports, if it doesn't burn evenly, it could cause structural damage. And it makes rockets a little less safe. But with this, it's a lot safer, and it's environmentally friendly right here. And on the right, we have a PEREGRINE rocket that we hope to test roughly 1 year from now at Wallops. In 2014, we conducted a test that shows that this fuel is both viable and stable and efficient, and it's able to fly in a flightway configuration. I also want to emphasize the advantage of this rocket, where it has the advantage of both a solid and liquid state rocket. With a solid state, you get a really high thrust, but it's on and off. You light it up, it lights, it burns, and then it's off. With a liquid fuel, you're able to throttle it. This hybrid rocket is able to do both. You have a liquid state fuel and you have a solid state fuel, and it's really efficient. So here we go. Beautiful, very complete. This was a ground test, so it's parallel to the ground, but you usually point it upwards, so we could go up. So we talked a lot about going up into space, about coming back down to space, or even other planetary bodies. Coming back down, it's really fast, it's really harsh, and it's a really hot environment. So we use something called a heat shield to protect our vehicle, our instrumentation, and our astronauts. And to simulate that, we have a facility called the ArcJet to test these thermal protection systems. Right now, you have a heat shield, and it's being put into the ArcJet right now. So typically, for us to quantify how well it worked, we measure the heat shield material before, and once that's done, we measure the heat shield after, and that's how much material has ablated. The material has to ablate to dissipate the heat. In the fluid mechanics lab, we developed a better way to do this, to actually see what's going on between the beginning and the end. We call this photogrammetric recession measurement. It uses the same technique as PIV, but instead of tracking molecules, you're actually tracking the surface of the heat shield being ablated away. Right now we have pica in the ArcJet. And one great use of this is, what if the ablation was uneven? Like, how would you know that measuring it before and after, and when it actually started becoming uneven? With this technique, you're able to see it in real time. And it's actually extremely hard to put any sort of instruments that would survive in this kind of conditions. And a lot of engineering also went into this. The surface right here is brighter than the sun. So, like I mentioned from the beginning, coming back into space, NASA Ames is also home to the world's largest wind tunnel. It could fit a full-scale F-18, even a full-scale semi-truck. But what better way to use it than to test parachutes? On the left, this was done earlier this year, is 2 out of the 3 parachutes that would be deployed on Orion when it comes back onto Earth. On the very right, you have the Mars Science Lab parachute. It's the largest supersonic parachute ever successfully designed, right over here. And what's incredible about this parachute in particular, it's taking MSL, or Curiosity, onto the Mars atmosphere. But when it's approaching the atmosphere, it's going about over 1,000 miles per hour. And it's the size of a Prius. And we have to slow this Prius down to about 200 miles per hour with just one parachute. Pretty incredible. I recommend YouTubing 7 minutes of terror on YouTube. It also shows you the other complicated techniques with zero margin of error, how to make this mission successful. Here we had a high-speed camera capture the successful deployment of the Mars Science Lab parachute. Of course, it slowed down. We had some problems in the beginning, but at the end, we were able to solve those problems and have a successful deployment. But did this work? Here's proof. I took it with my iPhone. So this is Curiosity landing on Mars, August 5th, 2012, and everything went flawlessly, and the mission was a success. Okay, so I talked a lot about supersonic speeds and breaking the sound barrier, but how does it look like to the naked eye on Earth? Well, I got a photo. This is the F-18 flying about Mach 1 over the San Francisco Bay. It's about 40 feet above water. It's a very daring pilot. And you can see the shocks coming off of here, or even the canopy. When shocks occur, it's usually a change of pressure and density. So that's what you're seeing here. I would call it a real-life Schlieren photo. But what does it sound like? Well,
Sound travels at about 760 miles per hour, or 340 meters per second. That's about 661 knots on an average day at sea level. And sometimes you can almost see it.
That's how it sounds like. Keep in mind, you're also hearing a lot of the engine noises that are coming off of it. But I definitely don't want one of these planes flying over my house at 3 a.m. So NASA actually has a Supersonics program in partnership with a lot of commercial companies such as Lockheed or Boeing and other entities, where we're trying to reduce the sound signature, boom signature, so it could fly over land efficiently. These are several of the designs that they have here. And this is for commercial planes. So one of you and I could fly on one of these planes in the next 15, 20 years. How amazing would that be? And so instead of going to New York, say, in like 5 hours, you're there in 2.5 hours. I'll definitely go to New York a lot more often if I had the money right here. And to point out, back here is a pressure rail. And that's what we're using to measure the sonic boom signature coming off of the plane. And the pointy nose and the wing itself all reduces the noise of that boom boom that you hear when it's flying over. So what about subsonic planes? What have we done for those instead of supersonic planes? Well, we've actually done a lot of work to make planes more efficient, part of the environmentally responsible aviation program here at Ames. One technique that we developed is called the sweeping jet. Right now, what you're seeing is the 40 by 80 wind tunnel with a full-size Boeing 757 tail installed. So these sweeping jets right here that you see has no moving parts, and about 30 of them are installed on these hinges, which provides us flow control. Because these are installed, it provides 20% more side force, which results in we don't need tails that big anymore for the plane to fly. So we could reduce the size tremendously, therefore reducing mass and drag and giving us a more efficient plane. This was a successful test, and they actually tested it in flight in April 2015 on an eco demonstrator right here. And that was also a successful mission. I suspect to be seeing these flow control on all future planes. Here's one test that's going on right now as we speak. I was actually walking next to the plane yesterday, putting it into the wind tunnel right here. It's the hybrid wing body plane. It's a plane that's both designed by NASA and Boeing right here. So environmentally responsible doesn't just mean fuel efficiency. It also means reducing the noise. So we have the engines on top. They're typically on the bottom. And this kind of shields the noise off the ground right over here. And this nice blended wing body gives us actually a lot more efficiency and higher cruise speed. You can see over here. And back to the aeroacoustics team, we also installed several acoustics array right here to measure the sound. Pretty great. This here is a special plane. It's a design that's commonly used, it's non-proprietary, and it's used all over the world. So this plane, you could use your computational method or your experimental method that you've developed in your lab or install different wind tunnels and go back to the database that everyone can use and validate your data or check if it's right or even close by. It's really useful, especially if you're not part of NASA, you really want to check your computational code. How do you do that? Well, you run it on the same model, right? And you can check there. We even done some work ourselves in the fluid mechanics lab. Right over here. So this is a semi-span CRM model tested in our low-speed test cell. And these blue streaks are actually oil that was applied. We turn on the wind tunnel, and we're able to see the flow field on the surface of the model, give us a nice visual effect of what's going on. On the left and on the right, we're measuring wingtip vortices. On the left, we use a Cobra probe, or a 4-hole probe that measures pressure along a plane. And on the right, in the same plane, we used PIV to measure velocities right here. So why is it important that we understand the wingtip vortices? Well, have you ever sat on a plane and wonder, the other plane has already taken off, why am I still sitting here? Why haven't we taken off? I can't wait to go home for Thanksgiving. My food's getting cold, right? Well, actually, wingtip vortices can be so strong if we're flying way too closely on the plane, on the next plane, it could flip another plane over behind it, which leads me to our next project. Here, we studied wingtip vortices and how to alleviate them using vortices coming off the tail, right here. So if one vortice coming off the wingtip going one direction, what if we had another vortice going in a different direction coming off the tail and basically canceling each other out? This did work, but the plane configuration was just not a viable plane configuration to fly, but it did prove that it worked. On the bottom right, the red shows one direction, the blue shows a different direction of the vortices. These are 2 vortices coming from the wing and 2 vortices coming from the tail. And let me show you how it worked. If we could find a way to get this to work, we could reduce airline traffic by an incredible amount. So we talked a lot about spacecrafts and aircrafts and air vehicles. We don't just do just that. In the last 15 years, we also studied truck drag. And wondering, why is truck drag important? Well, trucks consume 13% of the oil we use in the United States. And over 60% of that fuel on a truck is to overcome aerodynamic drag. That's a huge amount of fuel overcoming aerodynamic drag. So if we could even make it 5, 10, 15% less drag, imagine how much fuel savings we could have in the US. So here we have a side and base extender to cover up the gap. That also reduces drag. Another thing we tried is low buoy trailer, or we call it side flaps. Here, it could reduce the drag by about 10%. And if you want to add the trailer base flaps, it could reduce the drag by 15%, right over here. You can see a lot of this being implemented out there. If you drive on Highway 5 or even on 101, a lot of trucks have this. Most of them already have the side and base extenders covering the gap for you. On to the fun part. So NASA's mission is to inspire the next generation of explorers. So the next couple of slides, I'm going to show you student-based projects that we've done in the fluid mechanics lab. Here we have a fruit fly experiment that was done over 3 summers. It was pretty much solely an intern project. It was used to track and analyze how fruit flies flew in microgravity environment. But the biggest challenge was fitting this whole experiment in a 4-inch by 6-inch box. You can see here. Pretty great. This experiment flew up to the ISS last summer on a SpaceX rocket. Here, we've done a lot of sports ball aerodynamics, student-based educational programs. On the top left, you see a tennis ball that's not spinning, and we're injecting smoke into the flow. You see a very symmetric flow pattern on top and on the bottom of the ball. And here, we have a spinning ball spinning this way. So you have the wake going further out and the separation going further down. So this causes a downward force. Oh, it's probably easier to see if I show you a video of it happening. Here it's a baseball. Again, symmetric flow both on the top and on the bottom of this ball. And once it starts spinning, you can see how the flow changes. The wake starts coming right off further down, and you have the separation going further up, causing a sideward force. That's how curveball works. Upward force. So, fun fact, a tennis ball has the highest drag out of all the sports balls. Why is that? It's because it has the roughest surface. So we tested that as well. We have same tennis ball tested at different speeds. First is at low speed, you can see the filaments kind of sticking out, kind of hair, like hair on your arm, right? A really rough surface, high drag. We tested that same ball at higher speeds, but now all the filaments are laid down. Smoother ball, less drag. Okay, cool. How many of you have seen the World Cup? A lot of you. So the last couple of World Cups, there's been a lot of controversy on the soccer ball. Every World Cup, they have a new soccer ball design. It's not just for the looks of it. The aerodynamics is actually quite different, and that's because of the roughness of the ball. The roughness is determined by the length of the seams, how deep the seams are, and the pimples on the seam, and the pimples on the surface of the ball. This last year, it was the bazooka ball. It was a lot rougher than the previous World Cup, and therefore changing the aerodynamics. The goalies and the players were actually a lot happier with this ball, and we had no complaints this last year. I would recommend Googling or YouTubing bazooka or NASA. There's a lot of great articles about it, a lot of great videos to show you the work that we put into our research and a lot of the student projects to get students excited about aerodynamics with sports. So it's really great. And lastly, how many of you have seen Mythbusters? A lot of you. We have a few stars in the audience right now. So anytime Mythbusters has an aero problem, who do they come to? They come to the fluid mechanics lab. They've been here several times. When I was an intern, they were here twice. It was pretty cool. And they test all their myths. One of my favorite myths is the golf ball myth. So say I have a golf ball and it's dimpled and have the same exact ball that's completely smooth. If I hit it with the same amount of force, the golf ball goes twice as far. And that's because of the dimple on the golf ball reducing drag. So will that same idea work on, say, a car? If I dimpled my car, will I get twice the efficiency on my gas usage? Well, we had actually high school interns test that out here as well. And as a matter of fact, you actually don't get less drag. It actually makes it worse from our experiment that we've done with the interns. And right here, when they first came in, I think this was actually when I was an intern, they got a visit. I couldn't go. They got a visit Mythbusters up in San Francisco. So pretty cool. All right, questions? Thank you. Well, that makes it easier for me.
We'll have the center microphone in the aisle, so please filter around and ask your questions there.
I don't bite, I promise. Maybe a little. I have a question here.
Yeah, PIG, what is the code that you use for the partial imaging lesson?
Could you go to the mic and ask, please?
Yeah, my question is about the particle imaging velocimetry. If you just happen to know what code you use for that. And beautiful, excellent talk. Thank you.
Thank you. Is JT in the audience today? Laura Kushner.
If you don't mind repeating, please.
Sure, no worries. We tend to use Alleviation, which is a software package that is commercially available. Sometimes we do use in-house codes that we've written in-house if there's something special that we want to do with the data.
Oh, and one last question. Don't work in aeronautics. I like the SC picture of the fruit flies because that's the branch I'm in, the space biology branch. But I've just been told that the new winglets you see on aircraft are a recent innovation, and I wondered if anyone could address the aerodynamics aspects of these little winglet innovations.
The winglet's the one that goes on.
The little tips at the end of the wings that now go up that are I think, a relatively recent innovation.
Okay, Don.
On.
Go ahead.
So I'm Don Durson. I'm in the same branch as Christina. I'm lucky to work with her. She's a rising star in our branch. Winglets have been around for a long time, several decades. What's that? Okay. Stand up here. Okay. So just in case the recording missed it, I'm Don Durson. I work in the same branch as Christina. I'm an aerodynamicist there. Winglets have been around for a long time, probably a couple of decades or more. They've been tested on various aircraft, but there's been a lot more emphasis on trying to optimize them in their shape so that they really do improve the efficiency of any kind of aircraft that they put them on. You're seeing a lot of airliners now with winglets. Southwest Airlines has put winglets on all their 737s, and I'm seeing them more and more in other aircraft. Basically what they do is, their basic mechanism is that they give an effective span increase to the wing. Anytime you can increase the span a little bit, you're increasing the aspect ratio. That's lower drag configuration. The winglets also do help to distribute the wake vortex, or the wingtip vortices that come off the tips, and they do help to make those just a little bit weaker, and thus you're reducing the induced drag just a little bit. So it's kind of a complicated aerodynamic problem. But with careful shaping and integration into the wings of current aircraft, they are finding substantial savings in fuel and the drag reduction. So they are quite a great innovation. And they look cool, as my boss says. Thanks.
I noticed that you use a lot of scale models in these wind tunnels, obviously because you can't fit everything in there at once, but at what point does the scaling sort of interfere with the veracity of the measurement that you're going to be taking?
So there's a special number called the Reynolds number, and it's rho times the dimensional length, the size of it, divided by dynamic viscosity, mu. So if we're able to match this Reynolds number, you actually get the same flow field around these models, and we're able to have smaller scales. Can you imagine trying to test, say, a light real scale 737 and how much energy it would take for us and even to fit into a wind tunnel, which is why we go down to smaller scales to test these. A lot of the time we actually don't test in full scales in wind tunnels because they don't fit, but all our validation is done in small scale, and then we go into flight configuration for the final test. That's a good question, thank you.
If there's no further questions, please join me again in thanking our speaker.